Hello everyone, this is Fang Zhou. My presentation focuses on fault detection and diagnosis for residential HVAC systems using Transient cloud-based thermostat data. Introduction. What is the motivation for fault detection and diagnosis of residential air conditioning systems? FDD can help engineers identify specific operational problems, ensure a system is properly commissioned, predict gradual degradation, and prompt necessary maintenance. Therefore, home occupants benefit from reduced energy expenditures and increased thermal comfort. Manufacturers and service companies benefit from building a brand image for reliability and efficiency and long-term customer loyalty. The society has large amount of energy savings and less greenhouse gas emission. The traditional FDD methods are very commonly used for large commercial systems. They rely on installing multiple sensors on the equipment and typically need to collect both faulty data and fault-free data for training. However, for residential systems, the traditional methods are hard to apply because residential systems are produced in large quantities and installing additional sensors are too expensive. An alternative approach is to use smart thermostat data. In recent years, smart thermostats have been widely adopted by homeowners. They can record limited but important system operational data and then upload it to the remote server. Therefore, large-scale data analytics can be applied to the huge amount of data. The whole process for the FDD is as follows. First of all, smart thermostats record operational data in residential homes and then upload it on the cloud. Then, on the remote platform, the FDD methods start functioning by using statistical methods and artificial intelligence methods to identify faulty systems. After that, detected faulty systems are ordered based on the severity of faults. Given the list of systems, dealers notify customers who own the faulty systems, and service companies repair the prioritized ones as soon as possible. By this means, anomalous systems are identified by the FDD methods and achieve better performance after maintenance. Proposed statistics-based FDD method. The outline of the proposed method is as follows. The raw thermostat data is first cleansed to remove anomalous data points, then being partitioned and classified by the mode labeling algorithm. After that, important features are extracted. A part of the features are used to identify the poor tracking periods, which indicate system capacity degradation faults. And the other features are used in the statistics-based FDD methods to label faulty systems and characterize the severity of faults. Data partitioning and classification is performed by the mode labeling algorithm, which transforms the raw operational modes into three behavioral modes: regulating, tracking, and free response. A system is said to be in the regulating mode when the system cycles on and off and maintains a relatively constant temperature. A system is said to be in the tracking mode when the system operates continuously to reach the desired set point. A system is said to be in the free response mode when neither set point is active. This figure shows all three modes. The system operates in the cooling tracking modes when the temperature set point is decreased, then operates in the cooling regulating mode, then in free response mode when there is no cooling load. After that, the set point increases and the system operates in heating tracking mode. This paper researches the cooling tracking mode. There are mainly 4 types of transient behavior in this mode. The upper left plot shows a normal tracking period after the cooling set point is reduced. The upper right plot shows a poor tracking period, where the operational system failed to track the cooling set point. The lower plots show other 2 types of interesting behaviors that are not the main scope of this paper. This paper focuses on the poor tracking period. The poor tracking period is unlikely to appear frequently for a properly sized fault-free system, so it can indicate the capacity degradation fault. To identify the poor tracking periods, 5 features are extracted from the cooling tracking mode. They are the increase of indoor temperature, increase time, indoor temperature increase rate, maximum indoor temperature, and the degree hour above set point. The poor tracking periods have significant increase of indoor temperature, long increase time, and small indoor temperature increase rate. An unsupervised machine learning method named as hierarchical clustering is applied here to separate the poor tracking periods from other behaviors. After that, the degree hour and maximum indoor temperature of all poor tracking periods are averaged for each system. To exemplify the statistic-based method, the smart thermostat data from 10,000 single-speed cooling systems in Florida in the summer of 2019 is analyzed. These 3 plots show the distribution of the average degree hour and average maximum indoor temperature for the 10,000 systems. These 2 features can strongly indicate the existence or severity of faults. And this study takes 80% quantile of the 2 features in the distribution as threshold. Any systems with both features above threshold are flagged as faulty. Using this threshold, the regions on the plot considered as faulty are marked here. The reader should note that practically the real numbers of faulty systems are unknown, and the exact boundary between faulty and fault-free systems is indeterminate. But the threshold helps technicians to prioritize faulty systems for repair. In total, 68 of the 10,000 systems are flagged as faulty in this study. The lower 3 figures show the featured values of these 68 systems. Figure C shows that in most of these homes, the indoor temperature often reaches to around 29 degrees Celsius, although the cooling set point is usually set to around 23 degrees Celsius. And there are some extreme systems having very high indoor temperature and degree hour above set point. Figure D compares the previously defined degree hours with the degree hours when the indoor temperature is 2 Fahrenheit above the set point. The results show strong linear relationship, indicating that higher degree hours means high temperature and longer time. Occupants living in a high degree hour conditioned space have to endure high indoor temperature well above the set point value they selected for several hours every day. Figure E shows that the most faulty systems spend between 400 and 2,000 hours with poor tracking during the whole cooling season. Finally, one typical faulty system is illustrated. The first plot records the indoor temperature variation and the cooling set point changes. The second plot records the cooling on-off status. The third plot records the outdoor temperature variation. From this figure, the system frequently shows long periods of poor transient behavior. And the indoor temperature can spike from 24 degrees to above 30 degrees when the outdoor temperature is 32 degrees in the afternoon. Typically, every day, the system operates all the time from sunrise to sunset until the outdoor temperature drops below 26 degrees Celsius. It works very little during the night because the cooling set point is above the outdoor temperature and the house is cooled passively by the ambient environment. Conclusions. This study provides opportunities for novel FDD approaches using large-scale cloud-based smart thermostat data from thousands of systems. A statistics-based FDD method is proposed to identify the set point tracking failure behavior, which is possibly caused by inadequate capacity system faults. Faulty systems are detected by comparing features between a large number of systems. Behaviors of the detected faulty systems are shown by feature distributions and case studies. Thanks for listening.